So hello everyone and welcome to today's seminar. For today's seminar, we have with us Dr. Santamarina. He is a professor right now, professor in Georgia Tech. So basically, he is a worldwide expert about geotechnical. Actually, good part of his work that is a really contemporary research is still a classic piece of papers to read. Now, for today's presentation, we are going into a really specific. I saw this presentation in the Interpore conferences, and it's a conference about how the cyclic load can be understood into geotechnical, but also into other processes. And this topic can be interesting since we are nowadays facing problems regarding loading and unloading processes, mostly regarding storage, but also loadings in infrastructure. So I don't want to add anything more, just because Professor Santamarina asked, do not add in a lot. But yeah, now the podium is yours, Professor Santamarina.
Thank you so much, Daniel. It's a pleasure being here with all of you. And really, thank you for the opportunity. I think that this is one of the miracles of technology that allow us to be present at a distance, something that we should make more use of. So once again, thank you for the opportunity. And so next, I'm going to share my presentation. And let's see how that works. And I'm going to hide some of this. So bear with me a second, so things will be smoother thereafter. Okay, there it is. Excellent. So now I think that you should see my presentation on full screen. Let me know otherwise. But folks, the topic of the presentation is, as you see on the title, repetitive loads. And the geotechnical community has explored repetitive loads quite extensively for the last 60 years due to the Niagara and Alaska earthquakes. But that led to the whole field of earthquake engineering and soil dynamics and liquefaction studies, etc. That is not what I will be talking about. Of course, there is a whole people, the people in the transportation area, railroads and pavement bases that are subjected to repetitive loads, primarily of mechanical nature. And there is a wonderful richness in the literature related to that field. I'm going to be talking a little bit weirder cases, but I think that there will be a common denominator that will emerge, and so let's begin exploring them. Before I go any further, I would like to say that today I'm summarizing the research results of 20 individuals or more, and so this will be a very high-level presentation, and I invite you to explore their PhD thesis and publications that have come out of. And of course, I'm always grateful to all the funding agencies that have made this possible. So what are the examples that are going to inspire this presentation? Well, why do we use bone mass when astronauts go out in space for a long time? And what are the implications of breathing and heartbeats? And what happens when there is a major storm and there is changes in the atmospheric pressure, or when there are thermal cycles, or when we fill up a silo and we unload a silo, the foundations of wind turbines or a major hydroelectric project? What are the implications of all these cycles? And as you can see, the first ones are going to involve only fluid interaction. And then we're going to see the mechanical action for those of you who are more into geomechanics. And then I would like to highlight coupled processes. So let's start with the first set of examples. And this is really inspired by an old story whereby Kuhlman, you may have come across the name Kuhlman, trusses in structural engineering. He was in the audience when Meyer presented the structure of bones, a picture looking something like the one at the top left. And Kuhlmann said, you know, that looks like my cranes. The trusses that form a crane. So that means that the bone must be growing in response to the stress field. So this is the head of a femur. I hope you can see my marker, but otherwise we'll make it stronger. This is the head of a femur, where it goes into the coccyx. And you see the alignment of the cells longitudinally and transverse sketched here. So that was understood then, more than a century ago, but it was really not clear until 1974 when a paper said, you know, it is so important that we do exercise. And why? So imagine that the bone is made of the osteocanal and canaliculae that transfer the nutrients in and out of the bone to feed the bone, to maintain the bone alive and growing. And so what is the effect of mechanical action? Why does an astronaut need to be running with springs, holding it back to replace gravity, so he doesn't or she doesn't experience bone mass loss? Let's see what happens. Imagine that I have a red fluid invading a tube, and it goes in and out of the tube, in and out, and the red fluid invades, then it comes back, and the blue fluid pushes to the left, and vice versa. So nothing really happens. Now imagine that this is a canal, a tube, but there are large pores in the bones that is called canaliculae and lacunae. We use the Latin words, lakes and canals. And so the red invades, and when it reaches the pore, it puts some of the red in the pore and mixes with the blue, and you see that the color emerging. So then when it's pulled back, some of the blue actually comes with it, and more blue invades the pore, and then we push it back in, and some of the red that was in the pore now is pushed to the next pore. And all of a sudden, by going back and forth, there is zero effective fluid flow, yet there is transport of species. And so there is transport of a species with zero time average advection. And so when we do that, that means that when we superimpose a mixing process with an advective cyclic process, you can convince yourself, if you do carefully the mathematics, that this is beginning to look in some asymptotic approximation like Fick's law. The first time variation of the concentration is related to the second variation in space by the diffusion coefficient. And what is the diffusion coefficient? Mathematically, you prove that is the volume that you are injecting over the volume of a lacunae times the distance between lacunae squared over the period of the cycle. What a beautiful equation. It's a length scale square over time scale, the essence of diffusion, scaled by the relative volumes of injection with respect to the internal volume, the characteristic internal volume of our system. Let's see if this is true. Here there is a glass bead with water, and then we pull in and out water with methylene blue, and we always inject and extract the same volume, and you see that there is an effective diffusion front that is taking place, equivalent diffusion. And this is much, much faster than diffusion, so diffusion almost vanishes in that context, pure diffusion. And then you see, while diffusion is in the order of 10 to the minus 9 meters squared per second, these are much, much faster processes because this is the scaling relationship. So we can accelerate transport by injecting and pulling, injecting and pulling. Now, if that happens with chemical species, what about heat? Could I inject a hot front, leave some of the heat in the glass beads or in the matrix, pull the water out, inject new hot water in, and will there be transport? Well, first of all, we need to see that there is an internal time scale for not for mixing, but for heat exchange. So if you take a grain and you put a thermocouple inside, you dip it in hot water, and then you bring it to the cold water, there is a characteristic time for that grain to transfer its heat to the cold water, and that characteristic time in an exponential is the peak over the Euler's number, and that is a very characteristic time. So in this case, it takes a few seconds. So we want to inject water and to stay there long enough so the grains absorb the heat and pull it back out, and then inject back in, allowing for that internal time scale to manifest. Now, when we do that, and we do it mathematically, all of a sudden, we've reached to something that is equivalent to the diffusion equation, but now for heat transfer. Now we are in Fourier. And the diffusion coefficient is also scaled by the specific heat and the volumetric water fractions, but most importantly, is related to an internal length scale to the characteristic time scale of the cycles. Just so elegant. And we can very effectively transfer heat by doing that without having permanent advection. We did this with a column. The column has thermocouples all the way along, and indeed we conclude that that is the case. Now, there are other processes in our body that are interacting through cycles. For example, we breathe in, and in a cold weather like Alberta today, or even Atlanta today, probably the relative humidity in our heated rooms will be in the order of 40% or less. However, when we breathe out, that dry air goes into the lungs, and the lungs are saturated with water. That is where the CO2 and the oxygen get exchanged for the blood system. And so when we breathe out, it picks up not only the CO2, but also moisture. And the breath that we exhale is pretty much at 100% relative humidity. That means that every time we breathe in and out, we lose weight because of the CO2. CO2 is heavy compared to the oxygen, but we also lose weight because of evaporation. We release water. And if you measure yourselves before you go to sleep at night and when you wake up in the morning, you're going to see that you pretty much lose 200, 300 grams, and it's primarily water that you have lost. So we reproduce this in the laboratory. This is the granular packing in order to understand the atmospheric interaction with the subsurface, where the subsurface is unsaturated. And there is a very precise protocol that we do, and we measure the relative humidity coming out, etc. And we put the specimen inside the nuclear magnetic system so we can see the evolution of moisture content. And indeed, we have a very effective way of transporting moisture out of the granular medium, the atmosphere subsurface interaction, similar to our lungs. Now, something else happens in our lungs during these cycles. And for those of you who are in petroleum geomechanics, I think that you will find this of interest, but this applies to all unsaturated soils as well. In our lungs, we have something that looks like detergent. Detergent is a surfactant. And so what we have in the lungs, it has a fancy name, it's called pulmonary surfactants. Pulmonary refers to the lungs, surfactant, a detergent. And so these are the alveolus. That means the face of the alveolus, little balloons. The back of the alveolus is the flesh, and the internal hole is where the exchange takes place between the air that we breathe in and the composition of the blood. And so when we breathe out, now, by the way, remember the lungs don't have muscles. The way the lungs expand is we pull down the thorax, we expand the thorax, and so it sucks air into the lung, and then we squeeze the thorax, and that is when the air comes out. So every time when we breathe in, the alveoli expand, and at that point, the interfacial tension of the water on the surface of the alveoli is pretty much the interfacial tension of water in a glass of water, 72 millinewtons per meter. However, when we breathe out and the alveoli contract, all the surfactants come close to each other and they repel each other. So they bring the surface tension dramatically down, less than 10 millinewtons per meter. And that is very good, folks, because if we didn't have surfactants, the small, use Laplace's equation to convince yourself of what I'm saying, small pores would tend to collapse. But because we have surfactants, the surface tension decreases, and it doesn't collapse the pore. And so it's easy to breathe in again. And as we breathe in, the surface tension increases, and it's easy to breathe out again. Amazing self-regulation that takes place in the lungs by the changing in concentration of the surfactants. And this actually happens when water with surfactants invades the reservoir and is going through a pore throat. The surface tension decreases significantly. However, if instead of having these very small, significantly small molecules compared to small particles, if instead of molecules we had particles, now the particles would form a shell here, and the surface tension would go very crazy. Instead of being in tension, becomes in compression, and then you see that when a droplet contracts, when nanoparticles on the surface, actually it buckles as a shell. So there are lots of processes that happen every time we go through a pore throat in a soil or a sandstone or a shale. Now, there are many other cycles in our lungs, and they think happen, we can use it in natural and engineered systems. One is many cycles in our bodies. And the other one that I would like to highlight is the pumping of the heart. As you see, it's not very regular. And so it produces a high pressure pulse, and then it decreases the high pressure pulse and it decreases. Why does the heart work like that? You know, they have tried to replace the heart with artificial hearts, which are peristaltic pumps, just continuously pushing the blood, and the body doesn't like it. So why is it so important that we have these pressure cycles? Probably will take a longer time to discuss, but let me tell you some of the things that we can do in geomechanics. But before that, I would like to remind you that we do a cyclic flow. For example, when we swim, we move the arms very fast as we go back, and we bring them down slowly to the front, and then we swim fast again. And of course, nature does it so beautifully. And so let's see what can we do with this in our soils. Imagine that I have a tube, this blue tube here, and I put a grain here. Then with a syringe, literally with a syringe, I'm going to pump water fast. And when it goes fast, it drags the particle. Now then I'm going to pull the syringe back, but very slowly. Now at this point, the drag force is not high enough to drag the particle, so the particle remains. And then we pump again, we push the particle, and then we withdraw the water slowly. And we push the particle, and indeed we cause fines migration, and we can migrate propans, very, very interesting opportunities for hydraulic fracture and reservoir, preparing the reservoir for production. And we can do the same if you take a test tube. By knocking the test tube and counting on the contact angle hysteresis, I can move that droplet up, or I can move it sideways at will. And this is experimental data to show you. Cyclic effects on fluids are beautiful, folks, for mixing, for species transport, for heat transport, for moving particles throughout the system. Really exceptional opportunity. Now, many of you are in geomechanics, and that is an amazing program in geomechanics. So I'm going to jump now to a few examples on geomechanics. And we have to realize that the soil can experience different stress paths. So this is in tau sigma space, the QP. But it's basically shear versus mean stress. And it could be, how does a point feel on the side of a laterally loaded pile, or on the sides of a vertically loaded pile, or in a pile that is subjected to deviatoric loading and there is a fluctuation of the water elevation, or just repetitive loading on a foundation. So we have different stress paths. What happens to the soil? If you take the standard constitutive models, elasticity of course, but even if you take camp clay, once you push the yield surface out, then when you come back, you're done, you are in the elastic regime, so you cannot push the yield surface out anymore. So clearly this violates the fundamental constitutive models that we use in our field. And so how does it really work? Let me give you a few examples. And the first one is, if you do this in an odometer with zero lateral strain, you prepare a specimen, you load it monotonically in different steps, and then at this step, you unload and reload, unload and reload. And we go here through 10,000 cycles, and you see that the void ratio has decreased significantly. And then we keep loading, and the material goes back towards the virgin curve, but it has experienced this aging, this compaction due to repetitive loads. And folks, let me tell you something pretty earlier on here. The strain levels in each cycle may be very, very small. Each cycle may be causing an elastic strain in the order of 10 to the minus 5, 10 to the minus 6, and still leads to the accumulation of volumetric strains. Of course, if it is dense, these volumetric strains are going to be smaller than if it is loose, but still it is going to happen. It follows, this equation is really fitting most of this data, volumetric data, very well. It's a form of a power law. And so if you take the terminal void ratio, which is at an infinite number of cycles, it will go to an asymptote. All this process will have an asymptote at infinite number of cycles. And how do I know that? Because the volume cannot go negative. At some point, the volume of voids will decrease, but it cannot go less than zero. And in fact, it goes to a characteristic value for each condition and loading sequence that I have. And so I have these equations, and I can predict this propagation now quite well with these empirical equations. Now, what happens with the shear? We have to look not only at the volume evolution, but also the shear evolution. And shear is tricky, because while the volume will have to go to an asymptotic value, shear can continue accumulating in every cycle like a ratchet. This is the classical drawing from Leonardo. Every time you turn, it locks in the new notch, and it keeps deforming, and the same can happen to a soil. But let me give you a little hint. It will only happen when the amount of shear on top of the initial shear, this is the cyclic shear, on top of the initial constant deviatoric load that the system is subjected to, approaches failure. If you are far away from failure, you are not going to ratchet. You are going to go to an asymptotic state in shear as well. That is called shakedown. Away from failure, you are in shakedown regime. As you approach failure, you go into the ratcheting mode, and the shear strains will accumulate forever, and the slopes will continue going down. So I already presented monotonic loading in K0. I show you the case of a simple shear now. There are other ways to add changes in mean and deviatoric stress in soils, and one of them is by changing the pore fluid pressure. So we load the specimen to a certain deviatoric stress, we maintain the deviatoric stress, and we change the pore pressure, and it can bring the system to failure, right? But so we control how far or how close we want. And that is, by the way, what was going on with the foundation of the Tower of Pisa with successive pumping. And indeed, if we are close to failure initially, close to the deviatoric load approaching failure conditions, we are going to have very pronounced displacements and accumulation of shear displacement. So now, let's summarize what we have said out of these three cases. From a point of view of volumetric evolution, it has to go to an asymptote. You cannot have negative volume. So it will approach an asymptote, which is not critical state. Critical state, by the way, it doesn't happen really either, but critical state is an idealized limiting condition for monotonic shear. This is not monotonic shear, so it will approach its own limit state, asymptotic state. This is in volume. In shear, it can either stabilize at some point or continue accumulating shear forever, and that is the shakedown and ratcheting modes. If you follow what I just said, and these are the yield surfaces at the beginning, depending how far we are from failure, the strains will be normal to the yield surface, so it will be isotropic or it will be in the deviatory condition. But as I said in the last slide, after a very large number of cycles, you are not going to have any more volumetric strains, but you may still have shear strains, and so we're beginning to violate normality. So folks, we need new data sets, we need new models, we need new constitutive models, but we also need new numerical algorithms, so there is no numerical error accumulation. And so every so often we have to check with asymptotic trends to make sure that what we are accumulating is not numerical error. And as I mentioned in passing, you can accumulate the strains at very, very small cyclic strains, much smaller than the elastic threshold strain that came up from the liquefaction literature. I think of Dobry and Busetich or Ishihara's data, etc., or the project by Robertson and in Canada. We can have strain accumulation in cyclic processes. Of course, when we're thinking of 10,000, 100,000 million cycles, even if each cycle produces a very minute strain, and that leads to very beautiful physical discussions that we can address later on. So now to conclude, I'm going to give you some other examples. The third segment will be on other examples where the cyclic processes trigger coupled processes in our geomaterial. So let's take some examples. But first of all, we have to say, why is there coupling? There is coupling for two reasons. One is thermodynamics, energy conservation, and it says that nature will conserve energy. The other one is Le Chatelier's principle, and it says that nature will do everything it can to oppose change. If you combine these two, you convince yourself that all forms of energy are always coupled. And for example, if you take a rubber band, not all rubber bands will give you this effect in a way that you can sense it, but try a few rubber, they all do it, but you cannot sense it with your lips. But try a rubber band, stretch it and feel it with your lips, and you'll see when you stretch it, it's hotter than when you just started. And then if you relax it, you will see that it will be quite cold. Very clear, we have thermomechanical coupling, and in fact, we have all these other forms of coupling. And there are other forms of energy, and they're indeed all coupled. Let me focus on some of these examples. Now we have to think of what is the nature of coupling beyond the global macro-scale physics. What is the causality at the particle scale in soils? Well, we have to think of all the forces that act on a particle. The force that it has to carry for being part of the granular skeleton subjected to effective stress, the self-weight, the buoyant force, the hydrodynamic drag, capillarity, attraction, repulsion, thermoelasticity, and cementation. Now you see that all of these are asymptotic equations. I purposely wanted to get them in a power form, are either linear, quadratic, or cubic with the size of the particle. That means that when I plot these forces in logarithmic scale, they're going to have a slope 1, slope 2, and a slope 3, and the lines are going to intersect. What does that mean? Well, for example, the self-weight of a particle is equal to the capillary force that particle can experience until the particles are about 3 millimeters. Large particles, self-weight is more important than capillarity. You cannot pick up an orange with another orange just by wetting it. However, you can pick up a small grain of sand with another wet grain of sand because the capillarity at that point is greater than the self-weight. And that is the essence for sand castles. And I can do the same with all other forces and convince myself that there are different regimes where one force governs or other force governs. And to conclude the story and to make it simple, coupling effects are very important for starting with silt and primarily with clay. They're really not important or that important in coarse grain materials. So let's look at the chemical coupling, and because chemical coupling is relevant to the fine grain materials, let's understand why, and that is because of the double layer theory. And van der Waals attraction, something called DLVO, the first letter of 4 last names, which combines van der Waals attraction and double layer repulsion, and I can change it by changing the ionic concentration of the fluid. So now I can make cycles of high and low concentration, and you will see that silica flour experiences almost no strain. Kaolin will experience some strain, bentonite, quite significant strain. And of course, the higher the specific surface and the smaller the stress that the soil is subjected to, the higher this effect will be. So now let's do an experiment. This is an odometer filled with a kaolin specimen, saturated, and I run deionized water, and then I switch it here without changing the pressure. I run brine for many days. This experiment took 1.5 years, and we did only 6 cycles. And then I switch back and forth, and back and forth, and you see how the specimen begins to contract when you subject it to high ionic concentration, a little bit of expansion when you run deionized water. Contraction, little bit of expansion, and once the soil contracts, it's very difficult to expand, the same as during odometric loading. And so very clear the effect of, let's say, saltwater intrusion cycles on the accumulation of strains around the continental margins. What about wet-dry cycles? Oh, capillarity can be quite important in small grain soils. So we do the same. We take a specimen, we apply an initial load, and then we subject it to wetting and drying cycles, and very pronounced contraction. And then the void ratio decreases quite significantly. It follows a similar type of accumulation model. What about thermal cycles? For you guys, freeze-thaw, but now this is affecting most of North America. And so freeze-thaw gets a little bit trickier. And let me explain why. First of all, what happens with freeze-thaw is you begin cooling, then it stops cooling because you get phase transformation, then continues cooling, then during melting, it begins heating up until it melts all the ice, and then it continues heating up, etc. Very classical phase transformation data. This is a thermocouple inside the specimen. But if I look at the specimen, this is sand, saturated sand with ice. You don't see any ice lenses forming. Now, if I look at the same specimen inside the tomographer for a kaolin, I see all these ice lenses that have formed, almost like carrots invading the soil. In fact, the mechanics is exactly the same as roots, growing roots inside the soil. Now, what happens is when the water melts here, it just drains out. But when the water melts in fine-grained soils, it doesn't escape so fast. And now we have a water film, water layers, which make the soil very sensitive in the slope will come downhill. And that is what we capture in this sketch. This is the data that presents that, but I'm running out of time, so I don't want to dwell, but there are effects on shear and on volume, or in this case, on drain behavior will be on pressure. So finally, I didn't highlight this, but if you went back to the forces experienced by thermoelastic effects and the skeletal forces, both of them are proportional to the diameter square. That means that thermal effects will affect all geomaterials, thermal cycles, from a clay to boulders. Because the diameter cancels out, the effect is independent of size. And so let's see if that is true for large boulders. The idea is that when the sun hits the big rock mass, it expands towards the free space. Then when it cools, it contracts, but because of friction hysteresis, it will contract in such a way that the choke blocks will fall down, expands again, contracts again, the choke blocks fall down further out, and this block is gradually pushed sideways. And we see these folks, look at this wedge. Look at this wedge. This is moving. This is going to push it. This is not toppling. This is thermomechanical ratcheting. And look at these other wedges. And now you begin to find them everywhere. The famous Masada Mountain in Israel. Oops. And you see the choke blocks. And these are the formation gauges. And they see that it's indeed moving. And they thought it was because of rain, but it doesn't rain. It's on the Dead Sea. And this earthquake was not related to earthquakes. It's all about seasonal thermal fluctuations. And we see that once again in Saudi Arabia. Look at this block, it's moving. You can see the displacement that it has experienced and the choke blocks falling behind during thermal cycles. So we reproduce this in the lab. This is the choke block in the front. This is the other wedge at the resisting block at the front. And we subject it through thermal cycles by increasing the temperature and decreasing the temperature of the room. And you see the thermal oscillation that we created, and you see how the block is coming down as it happens. And yes, you can do the mathematics and convince yourself that thermal ratcheting will take place. Folks, we have come a long ways. We have seen the effects of moving the fluid back and forth, transferring a species, heat, even particles, causing the particle migration, and the effects of hysteresis in contact angle and surfactants and nanoparticles. Then we saw the effect of mechanical loads, and finally the coupled processes during cyclic phenomena. So to conclude, repetitive loads are everywhere, and they come in all forms. We have to pay more attention. That's a reason why your driveways are breaking. It's not so much because it freezes, but because it freezes and thaws. That's the reason why Canadian Tire is so smart that by August it already has the tanks of liquids to protect your driveway so the water doesn't get in to cause that crystallization. The causality is complex and depends on the cases, but it's strongly related to energy coupling, hydromechanical, mechanical thermal, thermal mechanical, chemomechanical, etc. But it's also intimately related to hysteretic response and asymmetric excitation. You swim more actively in one direction than in the other to have forward motion, and there is hysteretic response, for example, in contact angle. Be careful, because concepts that we have developed from monotonic loading may not apply to repetitive loading. I gave you one example of the threshold strain, but also think of the asymptotic deformation conditions. It's not going to be, let's say, critical state. We can capture always physics in nice dimensionless ratios. And then here is a combination of dimensionless ratios that came out from today's presentation. When you think of soils, for those of you who are strongly into soils, you have to think of two things. What will happen to the volumetric strains, and the shear strains? Volumetric strains will go to an asymptotic value and will vanish. What happens to the volume will go to an asymptotic value and the strain will vanish. What happens to shear? It may continue accumulating forever. And in fact, long-term monitoring of some slopes, you see how they are creeping, but really by cyclic motion, down like an accordion effect coming downhill. In the case of fluid flow, there is enhanced transport of everything: heat, vapor, species. Phase transformations, be very careful with them, particularly in fine-grained soils, because the crystal growth is grain displaced, while in sand is pore invasive and it doesn't affect the fabric much. Thermomechanical cycles, you have to expect them to have an effect on any type of soils. And so if you have a thermally active pile, very common nowadays, particularly in Europe, when you have both strong summers and strong winters, those will have a tendency to interact with the medium, and if they are heavily loaded, they could lead to ratcheting. And then I highlighted that in order to do this analysis and for engineering design, we need good test protocols that we don't have. We need good constitutive models that we don't have, and we need to have numerical simulators that we don't have in order to prevent error accumulation. And so there are a few groups around the world that are looking into this, but this is where the state of the art is today. I am truly very grateful to all of you for being here with me today, particularly Daniel for organizing this. And I just want to say a special hi to very close colleagues and friends, and Rick, Albert, Gonzalo, always looking forward to chatting with you. And so that was my presentation today.
Okay, thank you very much, Dr. Santamarina. Okay. So any question here in the room? Okay, give me a moment. We have a question. Give me a moment, I'm going with the mic. Okay, try.
Hello. Good. Hello, Professor Santamarina. Thank you very much for the wonderful presentation. We learned a lot from it. My name is Me. I'm working with Dr.
Sorry, we cannot hear you well. If you can speak closer to the microphone. Sorry to interrupt.
Yeah, no, we are. Min is moving. Give me a moment. She's coming. Okay. Here.
Thank you very much, Professor. My name is Me. I'm working with Dr. Albert Liu. Thank you so much for the nice presentation. So I just have a small question. In our compression test of the dense sand and loose sand, I'm wondering, so when we add the cyclic loading, after that, how much is the stress? I mean, does it influence our behavior, especially at the high stress level? Thank you.
Very good question. So the pure case of that test would have been isotropic loading, like in a triaxial test by changing the confinement. That would have been a better test. Yeah. And if that's the case, then it always goes back to the isotropic stress. But the question is indeed very perceptive. If you do it under zero lateral strain condition, you begin accumulating horizontal load. And so the K naught value begins increasing towards K passive. And so that is happening. And by the way, that happens in nature too, and not only inside your odometer. Nature is beginning to accumulate horizontal stress during cyclic loads. One more additional thing that I would like to point out here is when we do odometer tests, we don't realize the huge amount of friction that we mobilize on the walls. And they also accumulate, which creates a very complex stress field in an odometer. So an odometer is a lovely test, but its analysis is more complex. So working with large odometers and thin specimens is important in order to avoid some of these edge effects.
Okay, thank you.
Any other question? Okay. Any question from the people online? You can raise your hand and ask. you want to quit? Yeah, come here. Okay.
Hello, Dr. Santamarina. It's Albert here. Just kind of a quick question and not trying to get philosophical, but was the most of the the problem that you've described as we are facing this repetitive loading scenarios in the world of geomechanics, was that primarily driven by just the fundamental lack of measures or quantification parameter that we have for the soil fabric, and because we only have the void ratio, seems to be effective in a way, but it's only a scalar, and then we can't really interrogate much information out from a void ratio change along. And then I was just wondering, what would you be, what can you share some of the insights regarding that?
Yeah, very good question, and not a trivial one to answer. We gain information on the evolution of fabric, for example, in some simulations by Adrian Garcia on thermal cycles in granular media. And there have been a few other researchers who have done that. And so then you begin to see how heating and cooling, when a grain contracts, it creates local slippage, not global, local, for one cycle, and then in the next cycle, the next one, and then in the other, and then this process continues, accumulating both volumetric and shear strengths if there was a deviatoric load. That is the only way we can get insight into the fabric. Experimentally, you could do the test in a tomographer, let's say what Grenoble does. They haven't done it on repetitive loading as far as I know, but they can monitor each individual particle and see how it's rotating and deforming, etc. You can also get insights, for example, we did repetitive loading at very high stress, reaching 20, 30 megapascal, and some of them at the small, medium, high stress. And you see also fine generation, which also leads to fabric changes. So there are many manifestations. It is very difficult to assess. And so now that the issue is that the fabric is a wonderful concept to understand what's going on, but it's a difficult one to use for engineering practice, right?
Right.
I mean, we do know that we create different fabrics by compacting specimens in different ways, but how do you bring that to an engineering practice and for an undisturbed soil? It becomes trickier. So we need to identify proxy measurements that will give you reliable insight into how the specimen will evolve.
Okay, thank you very much for your insight.
That was a challenging.
I always enjoy listening to your presentation. Thanks.
Any other question? Any question from the people online? Okay, I guess there are no more questions. So yeah, thank you very much, Dr. Santamarina, for the presentation. And yeah, we are so happy to have you here, and you are welcome anytime you want. And see you guys next week. Yeah.
Thank you very much once again. I appreciate it.
Thanks, Dr. Santamarina.